let's begin the session. There are two speakers. Sriram is around. Has he come? Well, first speaker is Majumdar, my former colleague as well as friend. So he's going to have that long title, Quantum Gravity Effects in Binary Mergers.
Oh, it's wonderful to be back here. I spent the most productive decade of my life here at IMSC. Like Ghanshyam said, we were colleagues for a long time. And it just feels great to be back here. And I'm most grateful to the quartet of the organizing committee for giving me this opportunity of sharing my thoughts with you. I was never a student of AKR, as some of our colleagues are, but I did have the opportunity of meeting him every now and then in conferences and so on. And later, when I moved back to Kolkata, I tried to shadow him a bit because I wanted to get a hang of what he was like as a person as well as a physicist. And that was very revealing indeed. Shayon did a wonderful job this morning of reviewing AKR's entire academic work. And in that, he referred to a paper which was on the Schwarzschild singularity. Now, I speak about the paper because of the circumstances which gave its birth. You see, at that time, AKR had been fired by the IACS for non-performance as an experimentalist. He also had only a temporary position at Ashutosh College, which meant that when he was writing that paper or working on that paper, 2 years later, he had no future to speak of. Well, it turned out that he sort of managed to be rehired at IACS, but that was later. But what did he do? First of all, he was not interested in something fashionable at the time, where the authorities at IACS, especially Professor Meghnad Saha, wanted him to do something fashionable like nuclear physics, and he wasn't going to do that. Why? Because he was in love with GR, okay? Now, he also fell out, sort of, with Professor N.R. Sen, which I mentioned, because the philosophies of what they were doing was somewhat different, even within GR. So that can happen too. So what was he going to do? He looked at a paper by Einstein, which I mentioned was on a spherical distribution of clusters approaching the horizon of a Schwarzschild black hole. And Einstein had tried to give an argument that this set of clusters would never actually penetrate the horizon. They'll never reach the horizon, so to speak. And Einstein's paper ended with the remark that we have shown beyond any reasonable doubt that this is going to happen. Now, AKR was skeptical. Why was he skeptical? Because he was one of the first to realize that the so-called Schwarzschild singularity, the singularity associated in the standard Schwarzschild coordinates with the horizon, is actually a coordinate artifact. He was not able to find a good set of coordinates which will work on the horizon, but this is there in that paper. So he began his career as an honest-to-goodness general relativist by attacking a paper by Einstein when he didn't have a job to look forward to within 2 years. Now, I was surprised that he could do this because I couldn't. I don't know how many of you can, but I asked him directly, what gave you the courage? He said, well, you know, it's not courage because this is unreasonable, right? I said, yes, that's why I'm asking you. And he says that it's because we from Borishal have a bit of recklessness. It's genetic, you know. so I felt that sometimes being reckless does help, although I'm not recommending for everybody, certainly. Now, and this is no example of that variety. Okay, so this is an event with which we are all familiar, the drama on the 14th of September 2015, direct detection of gravitational waves at LIGO. And it's a remarkable matching between two observatories which are separated, space-like separated, if you wish, by 3,000 kilometers. And this matching is just absolutely mind-boggling. So this has amused and fascinated all of us who are interested in gravity. And of course, the question is, what causes this fantastic signal? is there a source for this? Of course there is, but what sort of source is that? Now, we also heard in Sumanto's talk that all the data is consistent with BBH coalescence, with binary black hole merger. But is there a smoking gun? And the answer is no. So there are a lot of papers, in fact, a whole industry, of what alternatives there could be instead of binary black holes. But we will not get into that. Suppose you are a believer in black holes, which I think most of you are, then you'd like to look for some corroborative evidence. And this is the question that comes to mind. If you have a black hole, then this beautiful theorem by Stephen Hawking on the horizon areas tell us that in any physical process, the cross-sectional area of a black hole can never decrease. Okay? That's this result. So I've tried to draw a cartoon there, and this is, of course, directly from, is this working? Can you see the spot? Because I can't. It's somewhere there. Yeah, right there. So this is directly from the Nobel Prize-winning paper of Roger Penrose, but this is my cartoon, which shows that the area does increase. The question is this corroborated by the LIGO-VIRGO-KAGRA data? Okay? Does it really say that this is happening? That the remnant area is bigger or equal to the sum of the two inspiraling black hole areas, if this is a black hole, okay? And the answer turns out to be yes. This is another very beautiful study, which I have happened to read quite recently. And there are many groups involved. There's this group by Issy et al., Maximilian Issy, and a lot of other very important people. Of course, the error bars are large, as you can see. But with 90% credibility, they say that, yes, this is indeed the case. But a later work in which Badri Krishnan, our friend from Penn State, now he's, of course, at Radboud University in Netherlands, he's involved, Shilpa Kasta. And there the pictures are much better. This is a much later work. And they look at waveforms, look at the masses involved, and they show with much better precision that this is the case. So it's quite amazing why this should not be considered as corroborative evidence that what led to the LIGO signal GW150914 is actually due to black holes. Okay? So I shall assume from now on that it is indeed due to black holes, although there will always be skeptics, and I don't have problems with that. We will accumulate better and better data, better and better analysis. So hopefully either the statistics will improve or it will be washed away by some very new dramatic evidence. Now a little bit of review, because I always feel that there's a bit of confusion, especially among young people who are beginning in this area, about the laws of black hole mechanics, which I've written down here. Although you see, Hawking's theorem is called the second law. It was actually the earliest to be discovered. So historically, this is the first, and then these two followed in this famous paper by Baring, Carter, and Hawking. And the resemblance with the laws of thermodynamics is inescapable. However, if you look at this paper, which very few do nowadays, you will see that they say, we see that there is this grand resemblance with the laws of thermodynamics. But how can that be? We are talking about black holes. Black holes are, well, some black holes, of course, are exact solutions of Einstein's equation. And then the Boltzmann law should tell you that there is no entropy, because log of 1 is 0. It's an exact solution. So therefore, they say in that concluding section that this must be coincidence. Okay? But there was this brash young graduate student, by the way, Jacob Bekenstein at Princeton, student of John Wheeler, who felt, no, this couldn't be. He just felt that these laws are too beautiful to be just cast away as coincidences. Okay? I mean, this is, again, something fantastic. I mean, I find that, how can a graduate student think so independently? Maybe Wheeler had a little bit of egging on there. I don't know, inside story what it was. But he said that, no, it can't be, because if you take Partha Majumdar and throw him into a black hole, his entropy goes into the black hole, and the outside entropy has decreased, and therefore can't happen. the second law of thermodynamics cannot be wrong. So black holes must have an entropy. And then, to be consistent with Hawking's theorem, area theorem, he said that this entropy better be proportional to the area of the horizon. Of course, he adjusted the units, but when he tried to adjust the units, he felt that the only unit which he could put in there without its having any dependence on the type of black hole you're considering was the universal constant, which is the Planck area, okay, which is written right here. Its Planck length is 10 to the minus 33. So up to a dimensionless constant c, this was Bekenstein's proposal out of the hat. He just says this is what it's got to be. No derivation. He tried to give a derivation based on the Shannon entropy in information theory, classical information theory. But what he said was the following, because of course you'll realize that there'll be other people, including graduate students, professors, who will say, what are the microstates? And that's where Bekenstein gave a beautiful answer to my liking. He said that the origin of the black hole entropy, because a black hole has nothing in it, it's just pure gravity, right, must be the quantum states of the black hole, of pure geometry. So he was saying something which actually didn't exist in 1970s, as far as I know. It's barely existing in some perturbative quantum gravity treatments, but what does it mean? Nobody knew at the time. So this was something which was very, very nice at that time, and I felt that it was quite revolutionary. And of course, if you try to combine, of course, you see, here there was this question of how do you then not associate it to temperature? And Bekenstein's paper ends with the fact that my concept is nice, except that it has some paradoxes, because if you put a black hole in a temperature bath, okay, which is lower, then the black hole must radiate, but nothing can come out of a black hole. Now, the response to that has already been achieved earlier by Leonard Parker in the context of cosmological horizons. He had shown particle production. And he was getting to work the same thing out for black hole horizons, but Stephen Hawking beat him to it. And he showed that this constant better be a quarter in order for this to match up with his formula for the flux of radiation. Okay, so from this, on this basis, this is what the generalized principle is. So the generalized second law of thermodynamics has the idea that in a world, in a universe with thermodynamics, the total entropy, the sum of the black hole entropy plus the external entropy can never decrease, okay? Again, just like this is also kind of postulate, it's a hypothesis. There is no proof. Now, of course, you realize that if the black hole entropy is just this, then there's no difference between the generalized second law and the Hawking theorem. They amount to the same thing because all the constants, etc., cancel out. So you could say that it's just a way of rephrasing Hawking's theorem. However, if there are corrections, okay, then of course there'll be something more to say on the basis of the generalized second law, which you could not get out of the Hawking classical theorem. Now, so this is what I would like to talk about, but before that, another sort of a clarification is that, you see, unlike in Bekenstein's time, we have now some very serious proposals of quantum gravity at various stages of development, none complete. There's no single complete theory of quantum gravity, but we have partial proposals. But I can then categorize these in two distinct classes, which I call background independent proposals and background dependent proposals. In the background independent proposals fall these, some of these you may have heard about. I'm sure some of you know about these things: loop quantum gravity, causal dynamical triangulations, spin forms, causal sets, and so on. There are many others. Similarly, in the background dependent proposals, there's, when I talk string theory, I should speak with trepidation because I don't do string theory for the last how many years, I don't know. I did do string theory when I was here for a brief while. Now, this string theory, I mean the old-fashioned first quantized string, for which you do have to assume a background. And then there's the Euclidean quantum gravity, the variety which was also discussed, Gibbons and Hawking, where they have to assume a classical background and then look at perturbations around that. So it turns out that in the background independent proposals, there's no assumption of a non-dynamical classical background spacetime. And therefore, it has a certain inherently non-perturbative character. Whereas for the background dependent proposals, they do look at perturbations around classical backgrounds. So they work very well for perturbative calculations. In fact, string theory, I remember I did that because I wanted to understand how come gravity is finite perturbatively. And that works really well for superstring theory in critical dimensionality. So that's a thing that attracted me to string theory those days. Okay, so here it is. Now, what we mean by a black hole, again, this is very classical, very well known, so I'll go quickly over it. So the problem is with the event horizon. We all talk about the event horizon because it's very convenient to talk about it from a mathematical point of view, but does it really exist? Because it requires, technically, it requires a global time-like killing vector. And it's hard to see if there is one, right? Equivalently, you could also say, as some people use this word, teleological, which is to say that you wait for everything to happen, only then you know whether there's an event horizon. Okay? And you can't do that. We'll all be dead before that happens. So is there an event horizon in space-time? We don't know. Astrophysicists use this idea of the apparent horizon. Most of, even the gravitational wave simulations use this idea of apparent horizon. The only thing about that is, well, there are two things. One is that it depends on spatial embedding. So you have to choose a time-like surface, and it's only when you have chosen it, it's, a time slice, a spatial slice. So it depends on your embedding, and going from an apparent horizon to the next apparent horizon is a discontinuous jump, which also creates technical problems. But I guess people who are really doing the numerical stuff know this very well, and they can handle it. So this may not be a real issue. What I'm going to talk about is another kind of horizon called the isolated horizon, which was proposed, as far as I know, by Abhay Ashtekar in the 90s, late 90s. What it is that this is basically a null, non-expanding inner boundary of space-time. So unlike an event horizon, where you can have Cauchy surfaces going all the way through, this is a different kind of a horizon. Sorry. This is a different kind of horizon. You see the spatial slices, M1, M2, et cetera, they stop on the horizon. So these are two isolated horizons separated by a dynamical horizon. This Eddington-Finkelstein frame picture looks like this, sort of looks like this. But you see the differences are that, first of all, you can talk about things quite locally. So the time-like killing vector field exists only on this part and this part. But when the horizon becomes active like here, exchanging or absorbing or accreting something, then it's no longer isolated. But these are well defined as inner boundaries of space-time. And there's a smooth transition from the dynamical phase. All this is proven in the papers that Abhay and collaborators wrote down. Okay, I guess I can still continue with my talk. Unless you're feeling very warm, then maybe you should. Yeah. Okay, so see, like I said, the generalized second law was kind of a postulate, so I thought I'll try to do a little bit better. But all I could do was sort of a heuristic, hand-waving kind of justification for why it ought to be true in a generic quantum gravity theory. Okay, and I'm going to sort of do this really ham-handedly, so my apologies to the chairperson and others who are experts at this. The idea is that I'm going to not talk about the asymptopia, because this is a very local description. I don't need to worry about what's going on at infinity. So I'll ignore the asymptopia, but basically I'm imagining that things are asymptotically flat, so things will work out, et cetera, et cetera. I'm also changing my notation a little bit because B is now just the bulk space-time, and the inner boundary I shall continue to call H plus. Somehow I can't see the point, the laser point. Can you see the laser point? I mean, it's a very faint laser point or something. I can't locate it. I have a new I here, which is cataract operated, so maybe I'm missing that. There I can, yes. Now, so what I do is I imagine that the Hilbert space has this decomposition, assume that it has this decomposition. Any state can then be expanded like this, where I do not require that this be diagonal, so there is possibility of a bulk boundary entanglement. The horizon, the Hamiltonian operator acts like this. It's HB acting only on the psi B and H plus acting only on the psi H plus. And we use this constraint, which is known as the Hamiltonian constraint, standard bulk Hamiltonian constraint. You should note that I'm not making any assumption that the Hamiltonian on the boundary, on the isolated horizon, satisfies a similar constraint. Because if that is the case, then I won't have anything to talk about. So here, if I look at the average energy, you can see it's completely determined by what the energy of the horizon is, the isolated horizon. And there is, classically at least, you can talk about the energy of an isolated horizon. And this dH plus is simply this quantity here. So I can do this sum and rewrite this expression like this. And if I now take an ensemble of such horizons, let's say a canonical ensemble, at some inverse temperature B beta, then the Z, the partition function, can be written as a trace. And now you can see that this trace is completely expressed because of the Hamiltonian constraint in terms of a partition function which is only defined on the boundary. So this is some kind of a holography, if you wish, that the boundary captures all relative thermodynamic information, and you can define the entropy purely as something that is relevant for the boundary, and it is therefore logical to assume that it will be a function of the area of the boundary, namely the isolated horizon. Okay, so this is just the first part of the justification. The second part of the justification is to imagine a situation where we have an inspiral for a binary black hole merger, black holes far apart. And there, of course, you can define the individual entropies. And then there's a merger of which I can't say anything because it's dynamical. And then you wait for ring down to happen, and everything after that settles down. And then, of course, this coalescence is going to result in GW emission, gravitational wave emission. But then you could say that there should be a generalized second law when applied to the previous foregoing ideas that the black hole entropy of the remnant, okay, together with the entropy of the gravitational waves should exceed the sum of the entropies, okay? So once you've come down to that level, you could then say that, well, second law of thermodynamics takes over, so then we have. So see, the thing about this is that I'm not arguing, right, that this is going to happen classically. I'm only saying that quantum gravity exists in whatever form. And so there is a way of defining black hole entropy. That is a well-defined concept here. And like I said before, if you have corrections to the area law, then this will have some novel consequences, and that's what I'm going to talk about. Okay, so loop quantum gravity, that's what I specialize into now, was invented by Amitabh Sen in 1982. He wrote a fantastic paper, which nobody reads anymore. It's called Gravity as a Spin System. I mean, the very thought boggles my mind, because before him, people had worked with the spinor formulation. That was the great work of Penrose and Newman. But nobody had thought of gravity as a spin system in physical terms. So it was incredibly imaginative of Amitabh Sen to think about it in 1982, when I was just finished my PhD. And he had also finished his PhD. So it was just his first postdoc work that he wrote this. Again, I think it's a bit of recklessness, because you see what it led to. Amitabh Sen quit physics. But fortunately, 4 years later, Abhay Ashtekar took it up. And Abhay, of course, is, as you know, a very rigorous person, so he polished it up, which Amitabh Sen was not very rigorous, or if he was rigorous, he was not in the manifest sense, if you wish. But Abhay did a great job, and Abhay also pointed out various technical aspects, which I shall not go into. But mainly, I'll point out that the basic degrees of freedom, or these global degrees of freedom, holonomies or Wilson lines, okay, of the connection. So already, Amitabha was working on the connection formalism rather than the metric formalism, which is the usual formalism. But the connection formalism has some great advantages. It simplifies some of the constraints in the ADM formalism. And then you have, so the canonical variables, the local canonical variables are the gauge fields, the A's, the potentials, connections, and also the electric fields, as they call them. They're actually densitized triads. And, but Abhay and others showed that the better variables to work with were these Wilson lines and also the fluxes. So the sigma here is just this wedge product, and F is any smooth group valued, rather it's Lie algebra valued smooth function on the two surface S, or through which we are calculating the flux. The two surface S is bounded by these edges of a network, right? So this network consists of representations of, well, it's not the full Lorentz group, which is an invariance of GR, as you know, the local Lorentz group, but you can gauge fix it, and one way of gauge fixing it is to fix it to SU2. So these edges, which I've tried to color code, carry spin, okay? So here it is. This is, you could say roughly, crudely, that this is what quantum space looks like. Quantum space is this network, and these holes are roughly of Planck scale size, and which is why you don't see it. You see a continuum, right? And we are all located on the graph, on this graph here. So the graph has spins, carries spins. It's an oriented closed network, oriented because of the spin property, closed because it must satisfy Gauss's law corresponding to SU2 here, the local leftover from the local Lorentz group. And the vertices are ordinary invariant SU2 tensors. So quantum states are all described in terms of such graphs. So you can see why Amitabh Sen, I always think of him as T2, that's how I call him, he thought of a spin system. This indeed is a spin system, right? It's a lattice, but it's a floating lattice. It's a floating lattice different from the lattices that you're familiar with in lattice gauge theory or condensed matter physics, which are fixed lattices. You see, you have other symmetries of GR, which you like the quantum theory to reflect, and one of them is diffeomorphism invariance. So spatial and temporal diffeomorphism invariance allow you only to have a floating lattice. It's like a fishnet, if you wish, in 3 dimensions. Okay? All these are, of course, completely cataloged. They're worked out. They're very beautiful books now by Thomas Tiemann and Carlo Rovelli, and also a wonderful review article by Abhay and Jurek Lewandowski. One of the consequences of this spin network basis, it's a discrete basis of a continuum, if you wish, is that geometrical observables like area, volume, etc., are now discrete. They have a discrete spectrum, and they also are bounded if you imagine that you're associating the area with the cross-sectional area of a black hole. Okay, so I shall go a little bit into that, not a whole lot. I think half an hour is gone or something. Yeah, okay. But that's all right. I still have some time. So this is, well, I've given myself a review because a reference because I found that perhaps I was the first to draw this picture in 1998. Later on, I found much better pictures than this. So this is my drawing. Please excuse me for the bad artistry. I'm not a good artist. But I was able to communicate the basic idea. You see, we are constructing a horizon, okay, taking the spins that are there in the bulk, the edges that are there in the bulk. So these edges which carry spin will, so if you have an imaginary surface like this, you don't really see this surface. What you see are these conical singularities created by these edges making punctures on this imaginary surface. And if you have enough of these imaginary surfaces, then you can approximate it by a continuum. So this is like a picture of what a quantum horizon would be like, okay? So that's what I've tried to see here. Now, on the horizon, this is again something that there are many ways to see. On the horizon, the pullbacks of the connection fields are shown to form an SU2 Chern-Simons theories. So there are, if you imagine that this is the horizon, this pink line here, this pink sphere here, there are Chern-Simons fields going on, and these spins which are inherited from the bulk now act like point sources, okay? So you have an equation here for the states of the Chern-Simons theory, right? K is the Chern-Simons coupling constant. This is the area at every puncture, the elemental area. This shows the distributional character of this situation, and this is a spin associated with each puncture. So this is a quantum equation of motion. And this is the key equation which you must solve to obtain information. So this, now you have a picture of the microstates, okay? You know what the microstates are. They are Chern-Simons states. There are states of a Chern-Simons theory interacting with point charges inherited from the bulk spin network, okay? How do you calculate the entropy? Well, what you calculate is the dimensionality of the Hilbert space of the system. So you calculate the dimensionality of the psi, which satisfies this equation right here. And of course, Mr. God, also known as Edward Witten, had given a formula for that, okay? And this formula had been derived in a completely new context, a different context earlier, prior to this work. And you see, this is the thing. I mean, I went from string theory to gravity, and I was familiar with this formula because I was doing string theory those days, and this was quite a formula. He had calculated this dimensionality exactly using certain rules known as fusion rules, which are like Clebsch-Gordon rules for systems with infinite symmetries. Yang-Baxter, not Yang-Baxter, it's the, I forget the names of the people now. Yeah, dealing with infinite dimensional symmetries, basically, which is there in string theory with conformal field theories. So Witten had written that formula, and you can do that with some modifications. That's what Ramesh Kaul and I did. The reason I'm sort of dilly-dallying on this a little bit is because this work was done here. Ramesh and I were here. And I was very happy with this because it's the first time I've tried to do something by combining ideas from two different fields. I've never done that in my life, you know. And this is perhaps a little bit of a lesson for the youngsters here in the audience, that you should not be overly restrictive to philosophies, to an ideology. Physics is not ideological. Physics is a little pragmatic. So if you can bring one idea from somewhere and put it there, even if it is a little hand waving and so on, do it and see where it leads to. See, because if things are hand waving, you can always correct them later on. There's always some more rigorous guy like our Ghanshyam here is very rigorous, and 3 minutes less. Huh? 3 minutes less. That's a joke, right? No, 3 minutes is a joke. The fact that he's rigorous is still very true because some of you were his students and know him. So what happened was that if you now take the area, the cross-sectional area of the horizon to be much, much bigger than Planck area, which is to say we are dealing with macroscopic black holes, as you see in astrophysics, for instance, then what you find is that indeed there are these corrections. So for very large area, you have a correction, but fortunately the correction is expressed entirely as a function of the Bekenstein-Hawking entropy. this need not have been the case. Okay? So this is another fact which I think Ramesh also was, but I think I was happier than him in some sense. So what are the signatures? Well, you have this, which I mentioned. You also see that the quantum corrected entropy is smaller than the Bekenstein-Hawking entropy for large areas. And you also can see that, the gate choices that people have made, some people said, oh, no, it's not SU2, it's U1, and this and that. Well, Rudranil Boshu, Kaul, and myself, and then Ramesh and myself later. Again, this work was done here. This was done when Ramesh came to Kolkata. So this was, again, an IMSC work. We did this to show that there's a gauge invariant way by which this correction would come out, okay? Of course, we did the calculation first for spin half, where all the punctures were carried, where all the edges making the punctures carried spin half. But if you do the higher spin calculation, you find that the coefficient of the log term does not change so long as you're looking at macroscopic black holes. However, our work does not apply to Planck-sized black holes. Okay, so there's a definite limitation. And people have tried to do that. And what they see is that if you go for Planck-sized black holes, then the solution that we obtained using Witten's formula, that itself breaks down. Because there we identified certain configurations of the Chern-Simons theory, which simply would not suffice anymore. Okay? So for Planck-sized black holes, I would say, from my side, all bets are off. Now, for those of you who might, I wrote to Dhiraj that I'll be happy with a post-lunch talk, provided the lunch is not too delicious, such that it puts people to sleep. And if that is the case, and you had a delicious lunch, I did. So obviously, if you fall asleep, if you doze off, I'm not going to blame you, okay? But if you suddenly wake up, you should not feel lost, because I here have a mnemonic device, which I'm proud to say I convinced Ramesh that this must be true. And it also relates to some very intuitive guesses by John Wheeler, whom Sharon talked about. See, what John Wheeler said was that in 1977, after his illustrious student had talked about black hole entropy, again, I can't look at, this is the uncertainty principle or something. So, yeah, okay. So take a sphere, okay, like a black hole horizon, let us say, and break it up into plaquettes which are roughly of Planck area size, and put a binary bit on each of these plaquettes. So that's the bit, binary bit. And this will lead you to the entropy, that's the it, okay? How does it do that? Well, if you have n to nh number of is the ratio of the full area of this horizon. Well, I have not used any property of the horizon, but it's the fact that it's a sphere, and you covered it with a net, okay, with plaquettes. So this ratio is nh, which is much, much bigger than 1. Then you compute the number of states, then it's 2 to the nh, right? Obviously, because there are 2 states possible for each spin. As simple as that. And if you take the log of that, you have something proportional to nh, and that's the area law. Okay? Log of that is the area law. So this was that simple. And of course, this insight, again, is brilliant. But I said, okay, then instead of that spin, just counting all the states, only look at the spin singlet states. So you can think of this nh to be some even number, half of which are pointing up, half of which are pointing down. Of course, that would be one configuration which will give you this. The other point is that gives you an m equal to 0 set of states, m being the total m, the azimuthal quantum number, when you do composition of spins. And, but that is not enough, because you see the m equal to 0 total spin also exists for the integral spins. You have to subtract those, because we're only looking at spin singlets. So spin singlets means total spin s equal to 0, total ms equal to 0, right? Now, the way you do that is by changing half of that to saying that I have one spin which is different, okay? So let's say one extra half, one extra pointing up, then down, and then the number is this. So you subtract by this because this takes into account all the integral spins. Now, if you calculate that, this is what you get. 2 to the power of nh, which is the it from bit result, divided by the factor which we found, okay? Okay, so now I want to come, so how much time do I have, Ghanshyam? I think, well, maybe you should take 20 minutes, yeah, a lot of time. So all this is old work. Yeah, okay. All this is old work. I want to tell you something new. What did I do with this? So when, you see, when GW 150914 happened, and after that there was 170817, all these are very exciting events for people interested in gravity. If you're not looking at it, then you're perhaps not interested in gravity. So this is very, very important. But what relevance does my work have to do with this? And I just felt that it's worth a try. So you look at, so we already know one thing. We already know that Hawking's area theorem has been corroborated to some degree. Error bars are huge. And you say, hey, wait a minute, you are going to do quantum gravity? What hope in hell do you have that it will have any relevance? Because look at the error bars in LIGO, even for the verification of Hawking's area theorem. They are quite large. Yes, that is true. I'll come to that. I'll have a disclaimer at the end. Now here, if you look at, so here I have some definitions. Again, what is happening? Yeah, there it is. So this is, so I call the remnant SBH, the Bekenstein-Hawking entropy, as SBHR. And the inspiral ones is SBH1 and SBH2, okay? So the generalized second law with the loop quantum gravity corrections, they look like this, okay? Now the total inspiral black hole entropy is SBHI, which is just the sum of the two Bekenstein-Hawking entropies. The change in the black hole entropy is this quantity, okay? And delta, so this is just definitions because these are the quantities which are measured or which are analyzed by the groups that looked at the LIGO-VIRGO-KAGRA data, okay? So in terms of those observables, when we plug that into this generalized second law, we get this one, this relationship, okay? Now here, when we get this is, so they do measure the SBHI, well, they measured the ABHI, the total area in spiral, and they also measured these quantities, the delta SBHI by SBH by SBHI and so on. This quantity has not been measured. But fortunately, in an earlier paper with Anaria Ray, I had made an estimate of how much this would be. So here we make these approximations. So first of all, of course, there are error bars, and this quantity delta SBH by SBHI, which is the same as delta area divided by total area of the in-spiral black holes, right? So that one has a lower bound and an upper bound. Okay, this is the upper bound, this is a lower bound, where we include the error bars which they have found. And when you do that, you get an exact inequality, which looks like this. We make certain approximations that if you have similar mass black holes, which is true for GW 150914, this delta 1, 2 SBH by SBHI square is of the order of 1%, which can be ignored compared to 1 in this formula. Hawking's theorem analysis shows that this quantity from the data is about 5%, so that's much less than 1. And our estimate, Anaria Ray and my estimate, that was done in a different context, we did this estimate, and that was also much, much less than this. So when you put these approximations into this formula, what you get is a simple looking formula that looks like this, okay? Yeah, so, so far so good. I haven't really done much, and it's not great technical work either. So what was it? But then I noticed the following, that if you look at the LVK data, Hawking's theorem analysis of course implies that the right-hand side, this quantity, is bigger than 1, which is a positive number. And the left-hand side is, of course, SBHI is large because we're dealing with astrophysical black holes, and that's much bigger than 4. So this one, from the data, the left-hand side is positive, and apart from the minus sign, everything here is positive. So it's a kind of tautology, which means that the data completely is consistent with what quantum gravity is saying. Okay? This, for me, I could not understand what was happening. Now, let me go on to the disclaimers. It's really weird. Obviously, the loop quantum gravity correction is logarithmic to the Bekenstein-Hawking area formula, which means it's exponentially small. Therefore, you have no hope, or you don't have the right to hope, that LIGO data will have anything to say about it. Because LIGO data, the error bars are huge, whereas you need accuracies of the order of 10 to the minus 64. So obviously to claim that, oh, I mean, this is, I know, a very jingoistic, some people might even make such a claim, but I would caution you that please don't make a claim like that, because it simply doesn't work. But what is fantastic, so there can be no claim at all that the analysis of LVK confirms LQG corrections to SPH. However, there's this issue of the algebraic sign. Now, to establish the algebraic sign, I needed no more accuracy than what these beautiful analysis of LVK data by these groups, which I showed at the beginning. Whatever their accuracy is also my accuracy. I don't need anything more. That itself guarantees the algebraic sign. So what is the sum total of this? Well, it says that the algebraic sign, so the coefficient, in fact, is unimportant. If you look at the formula again here, what this coefficient, see this coefficient 2/3, where is my, can't see it. Sorry, it must be my, okay, yeah. Some of these torches are better equipped. They have a bigger spot, so maybe you can get one of those. See, this coefficient is the LQG correction, right? But it's unimportant. This could be 420 for all I care. It's a sign here that matters, right? So this is the crucial aspect of this. And so any calculation, okay, where you have a log correction to the Bekenstein-Hawking formula with a negative sign is consistent with Hawking's theorem. But what if the QG correction is positive? I know that there are some calculations, I forget the names, maybe it's Bob Mann at Waterloo and Solodukhin in Russia, some people, I can't remember the names now. What if this is the case? What if, you know, the SBH, the black hole entropy is bigger, is the same formula with the C constant is positive? Then you can do the same analysis and show that now this is an upper bound by this quantity. And of course, both these quantities from the data are positive. So it could be that this is still consistent with the data, or it could be that it isn't, because that depends now crucially on the coefficient. Okay? So it could be that there is some tension for some values of C. Depends on the calculation. Now, is there a way then to discriminate it? I don't know. I haven't done that work yet. Maybe some of you will do. But it is clear that if SBH is less than SBH, capital BH, then I have no problems with this. Now, I end by saying that, yes, there is a caveat. I have used formulas which we worked out here at IMSC 20 years ago, or 25 years ago, which only took non-rotating isolated horizons, because it's only for such horizons that the results are robust. What if the isolated horizons is rotating, like a Kerr black hole? People have tried to do this. Even Ramesh tried to do some work with Kalyan Rama, who was a colleague here. But I must say that I'm not completely satisfied with what has gone on. So there is work to be done here as well. I have in mind an approach where I can do this, but it is still work in progress. Okay, so thank you very much for your patience. I guess I have not crossed the time. Okay.
So we have plenty of time for questions.
So can you just show the constraint that LVK has on this area change? You had the numbers, right?
I should have brought that.
Okay, I'm sorry.
I should have brought that down here. I left it here. Yeah, so come again, Shuvanta, what was your question?
Just saying the numbers that you had, the LVK had some numbers, right?
I don't mind losing weight, as you can see, but let's see if we can get there. Yeah, here. Yes, you see, so these are the results which I could gather. You see, again, I must say that I'm not a complete expert on this, so I sort of briefly looked at their paper, and this is all I could get. So, you know, this is what you can get too. All I can say is that this is much better. This, where is this part? I mean, this Kashta, Shilpa Kashta's work is much better than the Tucholsky, Isi et al. Work. So, but again, is there a gravitational wave expert here in the audience who can say a little bit more on this?
But I was just asking that you have some part of the plot which is shaded, right? There is a part which is black and a part
Oh yeah,
which
you
is
see,
white.
if you had a peak in the shaded part, then the area law is off, right?
Yes.
So I guess that's what they try to do, to try to have an exclusion idea. And this is well beyond. You can see that the peaks here, wherever this is, am I missing it? I can't see it somewhere. Oh, it's at the top, yeah. So these peaks are well beyond that. So that is the degree of confidence they have.
Yeah, but this second plot, I can see like the peaks are very close to that.
Yeah, this one, yeah, again, you see, these two differences come from using the various waveforms. And so it has to do with the use of these waveforms. You know, some of the waveforms are better suited for this analysis. So I must say that, yes, there are ambiguities here as well. But I don't have any more ambiguities than what they already have. This is all I can say. So if you believe in this result, you believe in my result. That's the only statement I can make. But Badri Krishnan is going to come to Bangalore, I think. Isn't that true, Spenta? Badri is coming for some school or something. And I can make you two get in touch, and you can ask him all the questions, because he's one of the authors of this Shilpa Kashta paper. Yeah. Okay?
Okay, thank you.
Spenta?
Yeah, Spenta.
Yeah, hi. You must be knowing that Ashok Sen had examined the one loop corrections to
Yeah, he spoke
various,
about it here.
Yeah, precisely.
In Kolkata.
But your numbers are not agreeing with those calculations.
Oh, no. You see, Ashok was very categorical. Oh.
No, I'm looking at his paper. I just wanted to know that this number that you wrote down, 3/2.
Yeah.
I mean, it's not the same as the number that is calculated from general relativity, one loop calculations.
No, you see, first of all, Ashok began his talk with the disclaimer that there is no string theoretic way of doing a microstate counting for a non-extremal black hole.
I'm not talking of all those complicated things.
No, you see, the point
I'm just
this is an
talking
important point. So the calculation that he presented,
Yes.
okay, was not his calculation. It was calculation done by the people I was talking about, and they have a positive correction. Now, this was already a point of discussion between me and Bob Mann and Saladukhin and so on when we wrote this paper 20 years ago. And they said, yes, we understand, because the two approaches differ, because one is based on a background and the other one is not. Ours is not based on a background. The Saladukhin Rob Mann approach is based on having a partition function which is an explicit function of the classical metric. Okay?
No, I'm
So
asking
there's no
something
way-
very simple, actually. Firstly, I mean, I perhaps don't have so much time, but I would like to understand the area of what you were calculating. Secondly, do you know how to understand general relativity from this point of view, or even Newton's law? can you derive Newton's law from this formulation?
Oh, you're talking about, now this is not a question about our calculation.
No, I'm just talking in general, actually. And
okay, the first
Lisa, because I asked you a very precise question about a coefficient, and I don't think you have an answer, really.
No, I do have an answer.
No,
The
but it differs, right?
different.
It differs. But it
They will
cannot be two different theories of gravity, right?
No, you see, like I said, there are two different quantum proposals. None is a theory of gravity yet, because none is complete. Okay? Now, these two different proposals give the different answer for black hole entropy. Now, in this, what I've shown is that perhaps there's reason to believe that our calculation is closer to data, although with the caveats I mentioned. Now, coming back to your question about the second point, do I have a classical theory from loop quantum gravity? Well, you can ask the same question about a field which you know very well, like quantum chromodynamics. How do you derive classical chromodynamics from lattice gauge theory? You have to construct coherent states. And you know that a non-Nebelian gauge theory construction of coherent states is very difficult. You have proposals, and you have to examine the proposals. Same here. So there are people who have made proposals of coherent states of loop quantum gravity. All of them, of course, lead to GR, but with caveats. So this is a subject which is not finished yet. This is the part which is not finished yet. Otherwise, I would have said, we have a full theory of quantum gravity, which we do not. All right? So I can only say I don't know, okay, to your question.
I was just asking even about Newton's law, I mean.
Well, if you get Einstein's equation, you get Newton's law.
Very
that
basic
every school
question.
child knows, right?
In physics,
I think we should have, this is a debate which can go on and we can certainly continue on. I will join the debate. But meanwhile, I think if there are other questions, let's have that.
Well, there don't seem to be too many questions. So maybe I've zapped the audience.
Because I would like to have that discussion outside, not here. Because it's open.
You think it will be a fist fight?
Others cannot join.
Yeah,
But it will be open.
Shayan has a
That's all I
question.
mean.
Yes, Shayan.
Please, San.
Your this 0.6 plus 0.82 and 0.6 minus 0.6.
Yeah, I know.
So what's the meaning of that? Is
Yeah,
there any
well,
meaning
you know what it means, right? I mean, this is something that means that the area of error bars are too large. So do you trust them? So I would say that I would only trust them because of this later work, which Badri and Shilpa and all these people did, which has definitely improved the error bars. Okay. So again, I'm not an expert on how to analyze the LVK data. It's a very detailed work done by various groups. But if you look at the drift of all those papers, then it seems to me that the area law has been validated to some extent. To the extent that it has been validated, my conclusions are right. But if you have new data coming up tomorrow, then I'm wrong. But that's good, right? Because then I have something.
No, but what does it mean by saying that it's validated to some extent?
With some degree of accuracy, which is perfectly well stated. That's what you mean.
Within that.
Within the error bars, yes. That's what it means.
Any other question? If not, let's thank the speaker.